Hello everyone, welcome to the class of Liu analysis. This video, it is mostly for the discussion on sequences, and to some of us might be new, the concept of Cauchy sequences. Okay, first of all, let's take a quick look on sequences. Sequence, it is like those simple right? These are very simple kind of sequences. And do keep in mind that the sequence we are considering, it is an infinite list of numbers. Okay, and also it's helpful to consider sequences as functions. It's a special kind of function, such that the variable it is only taking integer values. And I saw already have a new term popped on the screen. It's the concept of subsequence. So subsequence, you can take out the even number terms, x2, x4, x6, those things, or you can take out the odd number terms, x1, x3, those kind of things. They each form a subsequence. But do keep in mind, a sequence, it is infinite list. It is countable. It is countable. A subsequence is infinite list too. And again, it is countable. It is countable. Okay. That's a sequence. And then hopefully we understand, speaking of sequences, sometimes we may have limits. So this is the concept of limit. You want to be very careful about definition of the limit of sequence. Okay. First of all, we are considering a sequence. It is in a matrix space. Let's say x d. D is the distance function or the matrix of the space Okay. And then we do emphasize, especially this part, somewhat overlooked. Okay, this is so-called limit x naught. X naught got to be in the matrix space too, because in a little bit we are going to talk about the Cauchy sequence, and then we may run into a situation a matrix space may not particularly including those limits at all. Okay? But for the moment, as I'm saying, you just want to be a little more careful when we say the limit of sequence. It got to be in the same matrix space like where the sequence is. Okay, so that's a limit. Otherwise, I really don't think there's a lot to say about the definition part. And the only thing I want to remind you is this is an analysis class, not just calculus. So you will have to be very careful about definition, and you need to not only doing the calculation, you need to write the proofs. And I'm talking about the epsilon n language for sequences or epsilon delta language in a more generalized way. Do keep on trying to see if you can write out some simple proofs precisely follow the fashion like we are having on the textbook. Okay. By the way, divergence is easy enough, right? If we see a sequence is not convergent, it's divergent. Properties of sequences, and this is what we considered previously similar. Like if we consider if the sequence converges to a particular point, it has a limit in the matrix space. Basically says in every neighborhood of that limit, there are infinite terms from the sequence. And still, I want to say it's a good exercise to see if you can make write the proof, or maybe if you think it's not true, give a counter example. Then the rest, I think, mostly should be obvious. As a limit of convergent sequence, it is unique. If a sequence converges, it converges to a unique limit. Okay. Part C, if sequence is convergent, it is bounded. It is bounded. And also, I really want to say all those statements. I did not provide the proofs. You can find the proof on the textbook. And also, I would suggest give a try if you can write out the proofs for those statements clearly. And then part D, this is still related to the topic we covered before, the limit point of set. And this time, I hope you see it doesn't make sense. Now it doesn't make sense. If we are having a point which is a limit point of a set. And then indeed, that point, okay, it turns out to be actual limit of sequence. That also, I hope it explains why we suddenly, when we consider the limit point of set, why a single point it is considered a limit. And now I think it makes sense because it turns out to be the actual limit of a sequence, actual limit of sequence. Okay. And then I think I really don't have a lot to say. Somewhat when I prepare notes, I just put it there. The squeeze theorem, hopefully you still remember the situation. Basically, if we are having three sequences and one turns out to be the upper bound of the sequence in the middle, the other turns out to be the lower bound, namely in the fashion of x less than y less than z, and y, the sequence of y, it is sandwiched in between. And furthermore, we do assume x and y, the upper bound and the lower bound, they are approaching to the same. So there's no space left in between, right? Which really means whatever the things are, the sequence sandwiched in between, it will have converged to the same limit. It will have converged to the same limit. Okay. It will have to converge to the same limit. And there is a proof. There is a proof. And as I'm saying, again, it is a good exercise for writing proofs. And some other properties we take for granted, like a limit of sum, it is sum of limits. Limit of product tends to be the product of limits. Limit of quotient, it is a quotient of limits. Again, I would suggest you may want to consider, give a try if you can write out proofs for each of those statements. They are not necessarily hard or challenging, but anyway, they are good exercises. You understand the idea of analysis. Okay. The next part, it is concept of subsequence, and indeed we already mentioned the idea of subsequence. And the subsequences, they both are countable. They have the same cardinal number. You can make a 1-to-1 map. You can make a bijective map, okay, from the indexes of the original sequence to the indexes of the subsequence. It's a bijective map. And also do keep in mind you are going to keep the sequences in the same relative order. Okay. I'm saying if you take out x1, x10 as part of your subsequence, definitely you are not going to change the relative order. X1 still got to be at least stay before x10. Okay. You can take out the subsequence with a pattern, like the subsequence with odd number terms, or the subsequence with even number terms. And indeed, you can take out the subsequence without a pattern at all. But you still want to keep the relative order, okay? Like for example, x7, in no way it can move to x5. And so you are still going to keep the subsequence in the relative order. And I think that these are some properties of subsequence. If a sequence is in a compact matrix subspace, remember what is a compact space? Compact space, okay. And not only compact space, it's a compact matrix space. It is compact space with a matrix. A matrix is a distance function. It's a simple product, it is a distance function. And then if that is the case, which means there are some subsequences which were converging the sequences, okay, converging the sequences. And the second part, it is somewhat important, a very famous theorem from Weierstrass. It says every bounded sequence in Rk, certainly it works for the space of real numbers, and R2, R3, so forth, contains a convergent subsequence. This is a very strong statement. And also another theorem on the textbook, the subsequential limits. And basically we said a sequence may have many subsequences, right? And indeed, the limit of a convergent subsequence, it is called as subsequential limit. And accordingly, we may have multiple subsequential limits. So this theorem simply says the set of subsequential limits, it is closed. And if we are considering a sequence in a matrix space, And now it's the concept of the Cauchy sequence, a Cauchy sequence. In many ways, you may think a Cauchy sequence, it is convergent, but I really want to know, if you read the definition carefully, the convergence definition for a sequence, we emphasize it converges in a matrix space. If it goes beyond, outside the matrix space, we don't necessarily consider the sequences convergent. Okay, so this is the definition of the Cauchy sequence. Basically, we are also saying a very straightforward way. It is just simply said after some terms, basically all the terms will have to be really, really close. Okay, it doesn't matter if you only take out the first 10 terms, 100 terms, or you can take out 1 million terms if that's all needed. The real issue about the sequence, it's about the infinite side. There's no end. So the first 10 terms, first 100 terms, they don't matter. But in the end, eventually, after a while, okay, the terms of the sequences really got to be really, really close. Could it be sequence from, well, there's one gap, next to each other, or they are the sequence of terms after another 10 terms or 100 terms. It really doesn't matter. They will have to be really, really close. That's a Cauchy sequence. And as I'm saying, if you only think about the real numbers, Cauchy sequences are converging the sequences. But we do have matrix space, okay, in the definition of the convergence of sequence. And so I listed 2 examples. And the point is not every Cauchy sequence in a matrix space is convergent. And for example, if we consider sequence in the form of 1 over n, and it is convergent in the entire set of real numbers. But if we make a restriction for the matrix space, it's all real numbers without the element 0. And then we cannot claim the sequence is convergent in such a matrix space, okay, the matrix space of real numbers without 0. Another example, if we are considering sequence in a matrix space, it is of increasing rational numbers. Satisfying the inequality x squared less than 2, or I can say x less than square root of 2, right? And indeed, we can find a sequence really getting really close to square root of 2. But such a sequence, it is not convergent in the matrix space x squared less than 2, even though it is convergent in the set of real numbers. Okay, so Cauchy sequence is not necessarily convergent. But again, if we only consider real numbers, a Cauchy sequence is a convergent sequence. Okay, it is a convergent sequence. A little more definition. We talk about the set a lot. And now with the distance function or with the matrix space, we always have a matrix function, and then we can define the distance of the diameter of the set. The diameter of the set, roughly speaking, you can consider that is the largest, the maximum distance. But anyway, to be precise, remember we have open intervals and closed intervals. The interval is the supreme concept here, okay? As it is a set of all real numbers of the form, okay, from the distance function, and P and Q got to be within that set. And we take out the supreme of that set, and that is called the diameter of the set. And also, there's some general discussion on the diameter of a set, and this is the formal statement. And if we know the sequence is, let Xn be a sequence in a matrix space, and En consists of the points, well, the points from the sequences. And it is clear from the preceding definitions. I really took everything from the book. It states, it is clear, but you really want to give a try to see if you are convinced. This conclusion, it is true. Limit of the diameter of all those sets has to be 0. Okay, the limit of the diameter of all the sets, those sets form a sequence, right? The sets form a sequence. We are talking about the sequence of the diameter of those sets, the sequence of diameter of those sets. Okay, and a little more property of the diameter of a set. And well, I really don't think if I keep on reading will be very helpful. My purpose of this video, I try to summarize or try to point out something bigger or something new, if that would be helpful for you to make through the chapter somewhat in a quicker way. And by the way, I think honestly, the Ruling's book for real analysis or mathematical analysis, I don't think anyone could make one chapter easily in 1 week. It's going to take more time. But for this class, that's all we have. 1 week for chapter. We'll give a try. We'll give a try to see how it really works. Okay. A little more on the matrix space about a Cauchy sequence. Yeah, as I just mentioned, in any matrix space X, ever converting to sequence is a Cauchy sequence. This should be true, okay? And then if you want to say ever a Cauchy sequence is converting to, which is simply not true. You see this, we will have to add some, basically it is a reversed statement, but anyway, you have to be very careful about the wording. X is a matrix space and Xn is a Cauchy sequence. And then the sequence converted to some point of X. Okay. And again, for real numbers, this is a more generalized statement, RK. Certainly includes the set of real numbers or one-dimensional space. Every Cauchy sequence converges. Every Cauchy sequence converges. And a little more definition about the complete concept for matrix space. We say a matrix space in which every Cauchy sequence converges is said to be complete. Okay, it's said to be complete, which means there are no missing points. And also, if we look at the other example I just mentioned, clearly, you look at the real number set without 0, and there's a missing point there. It's not a complete. It's not a complete, okay. And also, we have the set of rational numbers such that x greater less than 2. It's not a complete. It's not a complete. It's not a complete. Okay. So that's the completeness of a metric space. What else do we have in this section? Oh, infinity. I really don't have a lot to say about the infinity. Just do keep in mind, sometimes we do write limit of sequence is infinity. Even I'm saying the limit is infinity, but anyway, I really want to understand it. It simply means writing this way. It simply says the sequence diverges to infinity, okay, diverges to infinity. Similarly, negative infinity, it simply means the sequence diverges to negative infinity. That's the convergence concept and the divergence concept. This part of the test, I really want to say this part, it doesn't look like, it should be look like the comparison test, Imagine if you have something x less than y, but x is approaching to infinity. So you cannot have anything bigger than infinity, which means y is approaching to infinity too. Okay. And in the discussion of series, we have the so-called comparison test. Really, it's the same idea, same idea. And then if we are having a sequence approaching to infinity or negative infinity, which really means, which is equivalent as saying the reciprocal of the sequence is approaching to zero. And also could be possibly one-sided, okay, one-sided. So I have plus minus there, plus minus there. And the next part, lim sub and lim inf, because in general, when we have a sequence, it's I think between likely or not likely, it's more likely it is not convergent. It is not convergent. Okay, but possibly we may have convergent subsequences. So with a new notation, we denote the set L. L as the set. It is a. Let me see. Let me try to see. Make sure. Yeah. A. It is the limit of subsequences of the original sequence. Okay. Did I misappear? I think I missed one side. The round. The curly braces here. I'll fix that after this video. Okay. And then the set of all possible sequential limits, it is L. And then we denote the supreme or lim sub, okay, as the supreme of the sequence. Lim sub, it is the supreme of the set of all sequential limits. Okay, sequential limits. And then similarly, we have the lim inf. Lim inf, it is the greatest lower bound. It's the inf of the set L. L is defined right here. Okay. It's a set of all possible limits of subsequences. And some properties of lim sub and lim inf. And it should be clear, if a sequence converges, basically it indicates it is the equivalent, okay, saying the lim sub and the lim inf the same. I have a brief proof, and again, don't take my word for it. You can try to see if it really makes sense. Okay, if it really makes sense. Lim sub, lim inf. A little more property on lim sub and lim inf. And I do have two examples for lim sub and lim inf. And if we consider the sequence of sign n, and hopefully see the infirm, okay, lim inf would be -1, and the lim sub would be +1. And the limit of sign itself, it's not there. It's divergent, right? It does not exist. And also, if we look at one similar example, I have a coefficient 1/n for sine n there. Okay. Now it's going to change the thing totally differently. Even though sine, it is still oscillate between -1 and +1, but with n in the denominator, it's making everything approaching to 0. So in this case, we are having a sequence such that the lim inf and the lim sub turn out to be the same. And indeed, we just mentioned lim inf, lim sub turns out to be the same if they are the same, which means the sequence has a limit. So we do have this limit of the sequence there. And again, I just figured out I have another type. I'll fix this later. Okay. Cauchy sequences. And more about the Cauchy sequences. Yeah, actually, we already talked about the completeness concept here, right? In general, a matrix space in which every Cauchy sequence is convergent, it is said to be complete. It is a complete matrix space. Okay. And clearly, R is complete, and indeed RK is complete. And also, we have a matrix space like such. This is not complete. There's a missing point there. And also, we have the set of rational numbers in the increasing order, such that x squared less than 2, as we mentioned, or actually this is the set of even for the entire set of rational numbers. Yeah, it's still not a complete. It's still not a complete. Okay. And just to summarize some conclusion we just made about convergence of sequence, a Cauchy sequence first. A Cauchy sequence must be convergent in R. And indeed, this statement really works for R2, Rk. Okay. And then very similarly, a bounded monotonic sequence in R. It is convergent too. It is convergent too. Okay. Monotone increasing theorem. Increasing theorem. I think that should be it for this part of discussion for sequences. And a brief list of concepts we talk about the convergence of a sequence, and then subsequence, the concept of subsequence, the concept of Cauchy sequence, and the concept of a complete matrix space. Thank you very much for watching. Let me know if you have any questions.